Yeah, this is a very nice thing to discuss today. Like we'll be talking about math proofs. So what will be our agenda? So we'll be talking about our guess. Like it's not a random guess that we will be talking about. It will be there is some rationale behind that, and we are calling that an educated guess or conjecture, to be talking about like what a lot of people say. So this is another thing is like how to accept or reject those guesses, because our guess that might not be true in the context that we are working in or whatever framework we are working in. There will be two techniques mainly that I will be bringing in this session, and upcoming sessions that can bring other techniques. So those techniques will be like to accept or reject. There will be one technique that is called induction, and the other technique is by contradiction. So this is our agenda for this session. So first thing that's very interesting. So here this is a circle with one dot here. So another circle with two dots. And like what we are joining those two dots. There is a line segment and it divides that circle in two parts. So you can see here there are two portions, mutually exclusive portions. And in the first circle, you can say that there is only one portion. That's the circle itself. And if we go with another circle with one more dot, again we will be doing the same. We'll be joining all the dots and we'll be having line segments. Again, we'll be like counting the number of portions, disjoint portions of the circle. Again, lastly, like we will be having one more dot, again joining the line segments and counting the disjoint sections of the circle. So here what we want to make a table here, number of points and the corresponding number of disjoint regions of the circle. As you can see that 1, 2, 4, 8. Now the question is, what about these ones? So like we are just guessing, like we are just finding some pattern here. So you can see here, these are powers of 2. So power 2 raised power 0. So just we are looking at it and we see that whatever be the number on the left hand side, the power is 1 less than that. So again, so what's the educated guess here? That might be, so our educated guess, if there is n here, so n number of points on the circle, so there will be, the power will be 1 less than n. So that is our conjecture here. We are conjecturing a pattern. So if there are n points on a circle, then there are 2 raised to power n minus 1 mutually exclusive regions. That is what we are conjecturing. And when it's like patterns, we are conjecturing the patterns. And the pattern, it can be found not only in mathematics, even if like we are talking with abstract quantities in mathematics and we talk about patterns. So patterns we can find everywhere in nature. So I live in Pallavaram. Every day when I go for a walk, I see flowers there, and I count the number of petals there. So number of petals, like you can see in the flowers, one of them, the middle one 5, and the left one I think it's 8. Like these number of petals, they come from a very special sequence that is called Fibonacci sequence. And this sequence, it's like each number is the sum of preceding 2 terms. So this is a pattern that we find in nature. And this Fibonacci sequence, it's not only Fibonacci was discovering this pattern. it was discovered in various civilizations around the world. In India, it came in form of, like, with the help of, when people were talking, some poets, Hemchandra poet, and music, like people were connecting the idea of this sequence with music. So the pattern that we can find in our culture, music, and nature. So it's not that we just discuss the pattern among the abstract quantities. So we were talking about like conjecturing the pattern. So like our task is, like, for example, one more, if we have to make a conjecture about the sum of 30 odd numbers. So you can see here 2 odd numbers, 1 and 3. We are talking about positive odd numbers, in fact. So its sum is 4, 3 odd numbers, sum is 9, 16. Do you notice some pattern? So we can have other examples as well if we are not, if haven't arrived at any conjecture yet. So you can see that these sums, they are squares of the numbers, natural numbers. So we are conjecturing here again, sum of first 30 odd numbers is 30 square. That's quite interesting. So this is a conjecture. We haven't proved that thing yet. And a conjecture may be true or false. So it needs to be like proved to say anything with confidence. It's a conjecture, not more than that. So to say beyond being a conjecture, we have to establish something with supporting evidence. So here, like, it may fail at some instant. And those instances are called counterexamples. So when we are saying that whatever is our educated guess or conjecture, that may fail at some instant. And if it fails at one instant, we can say that it is not true. It doesn't hold every time. So those examples are called counterexamples. So here, So I'm moving backwards. So what about the following conjectures? You can say that if I say that the square of any number is greater than or equal to the original number. So yeah, like we can see that 2 square is greater than 2, 5 square is greater than 5, but a number which lies between 0 and 1, if we raise the power, the number decreases, like you can see here. So this conjecture fails, and this number, this example on the rightmost, that is a counterexample for this conjecture. You can connect any 3 points to make a triangle. So what would happen if the dots are collinear? So we won't be able to form a triangle. So this is a counterexample again. So that is what we have. Like a counterexample can be an idea to show the falsity of a conjecture, or we have to establish some proof, and through the laws of logic. So some laws we were talking in the prior session. So we'll keep talking about logic, how they play their role in proofs. So showing proof is not easy all time. These are very simple, and like for some people these are some kind of naive examples that we are talking about. So there are some famous conjectures, like which an example it could be this number, like if you see this equation here, x, y, z, these are positive integers, and if we put n as 1, this becomes x plus y is equal to z. So we can find solutions. This triplets 1, 2, 3, it satisfies the equation, and n is equal to 2. So these you can have a lot of Pythagorean triplets which can satisfy this equation. What happens if n is equal to 3? There are no values of x, y, and z we can find. And this was a conjecture by a mathematician in 17th century, Pharma. So Pharma proposed this conjecture, and this was the conjecture. And it's not even n is equal to 3. It's n is anything greater than 2, such kind of thing happens. This was the conjecture, and it took more than 3 centuries to prove this conjecture. And it was proven lately in 90s by an English mathematician, Andrew Wiles, who got an Abel Prize as well after that. Not directly after that, he got Abel Prize, I think, in 2005 or so. But it was not easy. And this conjecture, it's not that Andrew Wiles had the only contribution in proving that. There are a host of mathematicians who had been working on proving this conjecture. Some of them, they proved for particular instances, but they couldn't prove in general. So so we can say that when you prove, this was a conjecture until it wasn't proved. So when it is proved, we call it theorem. So now it's called Fermat's last theorem. And Fermat's last theorem, it's because people say that it was written in the margin or the text of the book that Pharma was writing. After he passed away, people found that, and it was famously known as Fermat's last theorem. There is another Fermat little theorem as well that you might see in upcoming classes. So anyhow, you can see another pattern here. You can conjecture here. You can see that every number here, every even number is written as a sum of 2 prime numbers. So this is also a famous conjecture. This is called Goldbach conjecture, and it hasn't been proved yet. So there is no proof until now. So it's not easy to prove. So we are talking about how to prove a conjecture, and there can be several ways to prove it. So one of them is induction. And induction, what does it mean? I show something holds for n is equal to 1. This is my first step. Then I show that if it is true at any instant k, I also show at the next stage. It means that I can it seems you can relate it with you are just stepping above the stairs, and this is your first n is equal to 1, this is n is equal to k. And if you are on the kth step, then if you can go one step upwards, that means that is the second step here. So let me explain it more, how I can convince you that I can climb a ladder. So that's I will say that I can step on the I can put my step on the first step of the ladder, and then I'll show that if I'm anywhere I can move upwards. Then I can show that I can climb the ladder. So you can see here, these two things, these 2 bullet points, they suffice us to say that we can climb the ladder. So I hope it makes sense. If it doesn't, we will be having a couple of examples. So then we can say that this holds for all n. Of course, natural numbers, they are. So it's a kind of a domino effect. You are just doing this thing, and one first card fall down, then it will make the upcoming cards fall down. So that's a kind of domino effect that people talk about. So this is mathematical induction that we say. So there are several, if we go by an example, this is a very famous example. If I say how to show that this thing j 1 to n. This sigma means sum, like we will change the values of j from 1 to n, and then we can show this thing. Like how this can be shown, like I just say, like I will prove it for the first case, like when n is equal to 1. This is our first thing. When n is equal to 1, then this becomes j1 to 1. It means like on this side, if n is 1, then I'm just plugging the value of n, 1 into 1 plus 1 by 2, and it's only one term here because j has only one feasible value it can have. So it's 1 here and it's 1 here. LHS is equal to RHS. So that means it's true for n is equal to 1. So we can do we assume that it is true for, this is our assumption. That is our next step. We assume that this is true for n is equal to k. And we prove that we can step 1 upward. So we prove that to prove for n is equal to k plus 1. So I'll just complete this thing. For n is equal to k plus 1, if I write k plus 1 in, I hope it's visible. J is equal to 1 to k plus 1. It's n into n plus 1 by 2. We know this thing. Using this information, we will prove this thing. So what we do, we know this thing, so we'll make use of this information. Why not we break this thing? Break this thing into two instances. One instance when j varies from 1 to n. Sorry, I shouldn't have written this thing. This is j here. So this is j here plus j is equal to, so that's the only one case left. And what is that? J is equal to n plus 1. There is only one case. There is only one case. I'm just writing here k plus 1. It's k. K, and it's k plus 1. I hope it's making sense. So, and this is what we know. This is what we know because we have assumed that for n is equal to k, this holds. We just change n by k, and just it's very simple now. It's k into k plus 1 by 2 plus k plus 1. And it's now like we can take it as common, k plus 1, and this will be just k by 2. It will be k plus 2 by 2. So now when n is equal to k plus 1, so it's the same thing. So it is your n, and this is your n plus 1. So that means we have shown that if this thing is true, so this thing also holds. Like, so it's a kind of domino effect. So like I did this thing, and once it falls down, so the upcoming card will also fall down. So in this manner, all cards will fall down. So this is what we call induction. So we can have a lot of problems. You can have the second problem as well, but we are not going to do that thing here. And the second problem that brings that doesn't bring directly though. So the right hand side, that's a Startling approximation formula. So, but anyways, we are not going to discuss that. So any questions? What questions you have? Yes, please. Okay, so there is another thing that I want to bring here. So this is again a very important thing, contradiction. Like if you want to show something, I want to show something. If I want to show that something, this thing, like we were talking about statements, P statement, yes. Oh, yeah, please say.
Consider
they can be same. We haven't said that sum in which the primes, they may not be unique. That sum can be expressed in different ways. Yes. It can be 2 plus 2 is equal to 4. So we didn't say that will be a unique expression, and there can be more than one way to express. Yes, please say, yeah.
Why do you call it as a conjecture?
Conjecture.
Why do we call it whole that is conjectured and even numbers represented as a sum of 2 prime?
Because we haven't been.
All prime numbers are weighted and 2 is odd numbers. So adding odd and odd will always be an even. So it can just be as a 2.
Yeah, but you have to prove no matter which prime number you have. Like we do not know all prime numbers.
How can there be a prime number that is multiple?
Yeah, sum of only 2 is the only prime number which is even. Apart from that, every prime number is odd. And if you add them, you will definitely get an even number. But we are saying the converse thing here. Like taken any even number, you will get 2 prime numbers. We are not saying that, yeah, of course, if we have prime numbers other than 2, their sum will be even. But will all even numbers will come on the right hand side as a sum? We are like, that is what that conjecture is saying. Yeah. Anyone else? Yes.
Sir, if we assume that n is equal to k in that question, can we assume as n is equal to k plus 1 and can we prove as n is equal to k plus 2?
Sure. K is just a symbol. It can be anything. If k is a random symbol, then k plus 1 is also a random symbol. What we are doing, like we are assuming for any random symbol and we are proving for one step ahead of that thing, what we had assumed. It can be anything. If we k plus 1, we prove for k plus 2. That is fine. Because this is mere symbol. Like k can take any natural value. Yeah.
Yes, so this principle of induction, thing we just did here, applies only to natural numbers, right?
Right. It applies, yeah, that is one important thing that we can say here. Like when we talk about induction, some people assume that like we are proving, of course this thing will be true for every natural number, but that doesn't mean that it will go beyond infinity. Like we are just talking about natural number. We are going one step ahead. If there is a ladder with infinitely many steps and we have capacity to take one step upward, but having this capacity, we may not be able to climb the whole ladder that is infinitely step long, because we have a limited power. One step, but it won't end. We'll keep doing that. Yeah.
So in this case, we have only steps because the sum value can only take natural numbers.
Yes.
But if it's like continuous, there are no steps, then you can't use this.
Right. Exactly. Induction is like for positive integers. Yeah. Right. Here, that's what we are talking about. We are not talking about any like. Otherwise, this summation makes sense for natural numbers or integers, like you can say. It doesn't mean that when we write this thing, j is equal to 1 to 1.2, like traditionally it doesn't make sense. But you can give meaning to it. That is up to you. But traditionally, usually, when we write sigma, that's a discrete kind of thing. And those discrete points are normally natural numbers or integers. I hope this makes sense. Yeah.
So we can't take k as significant as
K as?
anything else
anything else. When we use this symbol, sigma, then there will be, like, you will be discussing integral kind of thing when you are talking about things lying in between. So you will be like having a more generalized version of sigma when you are talking about integration. So we are not talking about integration now. This symbol is traditionally reserved for integers or natural numbers. Okay, so we were talking about contradiction. When we want to show, like we can do this thing as well. Like we have, I think it should be meaningful if you talk about the second example as well, because we have time. So if we want to show this thing, n factorial means like 1, 2, and it's like multiplication up till n. So where n is like greater than equal to 1, like something like that. And can be, people define 0 factorial is 1, that is also the case. So, but if you want to prove it, n factorial less than equal to n raised power n, how to prove this thing? What should be our first step? So we'll just, for n is equal to 1, we will prove this thing. N is equal to 1, check whether this thing holds or not. We put n is equal to 1 factorial less than equal to 1 raised power 1. So yes, this holds. So for this thing it is true. Then what is our next step? Our next step is we assume that it is true. We assume true for n is equal to any random symbol k. K is an indicator. K can be anything. And what will be our goal? Our goal will be, this is our aim, that to prove true for one step ahead. So this is our goal. So we plug the value n k plus 1 in here and check whether this holds for this thing or not. So we will just like put here what we know from here. We know that what information, this is the information that we have taken. It is k factorial n is equal to k less than equal to k raised power k. And what we want to show, this is our goal. This is something kind of given or we have assumed. So we put n is equal to k here, k plus 1 factorial. We want to prove that less than equal to k plus 1 raised power k plus 1. So using this thing, how to use this thing? How?
So multiply k plus 1.
Yeah, k plus 1. Oh, here. So yeah, that's nice. Multiplying k plus 1 on both sides, then the left hand side will become k plus 1 factorial. So that is something what we really want to show. So multiplying k plus 1 on both sides will be having k plus 1 multiplied by k factorial, k plus 1 k raised power k. So I think you won't be able, I should write bigger. So I will multiply k plus 1 on both sides, k plus 1. So what we want to show? On the right hand side we want k plus 1 raised power k plus 1. How to do that? Yes.
So we can claim that k power k will always be necessarily lesser than k plus 1.
Right. Yeah, right. Great. So we can do, yeah, as you suggested, we want k plus 1 here. So what we will be doing here, k plus 1, we can write, if we replace this thing by k plus 1, then this thing will be bigger. So k plus 1 raised power k. And if we replace this k by k plus 1, it will be more big. So it will be k plus 1 into, I think we are done. That is, we don't need to do anything else. K plus 1, done. So this was our goal, and our goal is accomplished. So like this sort of thing, like this formula written over here, it means that n factorial that approximates with under root 2 pi n upon e raised power n, when n is very large. When n is very large. So this formula, this is like if you have like some people write, there is a very famous limit, I think, where you can use it. I think this is the question. I don't remember exactly. I think this is what like people generally consider. I think in 11th, 12th class, when there is a concept that you can use this Startling. It's like you would wonder how did it come, and I was just like just trying to relate this inequality with that Startling approximation, and now I'm just mentioning an application of this thing. So if you are like not aware of limit, that's fine. So any questions before we move ahead? So we'll be having the last thing. So the last thing that we will be having, that is also very interesting. Like for example, there is a very famous theorem that the number of prime numbers are, how many prime numbers are there? Numbers are infinitely many. Like through this example, I will explain the next way of proving things. So, and this is a very famous way of proving. So, what we do, like this is my goal. I will deny my goal. I will deny what I intend to show. So, if I deny, what would I say that? They are not infinitely many. It means that they are finitely many, and we can list them. We can list all the prime numbers if they are finitely many. So we will say that, so I deny it. Deny this statement. And I would say that there are finitely many, P1, P2. I'm just listing all the prime numbers. So, and they are finitely many, I can say that, suppose n prime numbers are there. Not more than that. So, there are only so many prime numbers. So then what I want to do here, what is my strategy? That is what I want to explain through this example. And like what I want to do, I want to show something that I have made a mistake. And if I make a mistake, and then I will say, what could be that mistake? I just want to arrive at some contradiction, something that doesn't make sense. Then I'll say that, oh, what I did, I denied. So denying would be my wrong step. Then I'll say I shouldn't have denied. So this statement is true. So denying this thing would be wrong. So this is what my strategy. So these are the prime numbers. What if I multiply all of them plus 1? This is a number. I multiplied all the prime numbers plus 1. What do you say about this number? Is it divisible by P1? It is not divisible by P1 because this thing is divisible by P1 and plus 1. It means that 1 is acting as a remainder. And this thing is also divisible by P2 plus 1, remainder 1. So that means this is neither divisible by P1 nor by P2. And this happens with all prime numbers. It means that there doesn't exist any prime number in our list. And that list is like, what was that list? All prime numbers. It means that there is no prime number less than this thing. And that's the full list. No prime number among them can divide it. So it falls in the category of prime numbers itself. So because there is no number less than this number which is dividing it, that means this is itself a prime number. But if it is prime, what's the problem?
The last prime is Pn.
Yeah, like there will be some number which is like, whatever be these prime number, this number will be greater than all of these. Yeah, do you agree with this idea? This thing? So this thing is greater than, it is greater than all of them. P1, P2, Pn. So we have found a prime number which is greater than all prime numbers. That's an absurd. How is that possible? We had a full list of prime numbers, and through this process we found another prime number which is greater than all prime numbers. That means there is something wrong, something which is contradicting itself. It means that what we assumed, that was a wrong step. Is that okay? So it means that denying this thing was my mistake. If denying was a mistake, then there is, like, I have to accept this statement. So this way of the approaching solutions or proving something, that is what we call going by contradictions. Like we are, so by contradictions, this is another way. This is other than the induction way of proving things. So these are some standard general way of approaching proofs. So this is one of them. So what we did, we denied what we wanted to show, and then we arrived at something which doesn't make sense. And then we realized that we made some wrong thing. So there are a host of examples, and you have done those examples. One of them is a very famous example that root 2 is not rational. Root 2 is not rational. That thing you must have done through this approach. So what we do there, if I say that root 2 is not rational, so I deny this thing, and it means that if I deny, root 2 is rational. And my goal is to arrive at a contradiction. So if root 2 is rational number, by the definition of rational number, then root 2 can be expressed by a ratio of integers. Of course, denominator should not be 0. And further we assume that P and Q, they do not share any prime or any factor. So they are relatively prime. P and Q, their GCD is 1. So that is what we have assumed. What we have assumed? That GCD of P and Q is 1, and of course Q is not equal to 0. So that is what we have got here. So what can be done now? So we have this thing. What can be done? I square both sides, then it will bring 2 is equal to P square by Q square, and P square is equal to twice of Q square. And from here we say that this is an even number because it's 2 is here. If this is even, then you must have done one more thing. If an integer square is even, then that integer is also even. Because 2 is kind of an atomic number. You can further break it. If 2 is coming in factorization of something, which is factorization of square of something, it means that it's not that 2 can be broken. 2 is a prime number. 2 is kind of an atomic number. So atomic, when I'm saying, I'm not saying that, yeah, of course, atoms can be broken. I'm not talking about neutrons, protons. So I'm talking like it can't be, it's a prime number. So if this is even, so it means P is even. If P is even, 2 comes in the factorization of P. 2 comes at least once. 2 comes at least once. So then I just write, if this is even, so can I write that, suppose this is equal to 2k. P is equal to 2k. I'm just writing roughly. So if it is 2k, then I just write this thing here. What will we be having? 2k square is equal to 2q square. So this means 4k square, 2k q square. So that means q square is equal to 2k. What does that mean? Q square is even. If q square is even, then q is even. But what can we infer from that? So if q square is even, then q is also even. And if q is even, p is even, how can they be co-prime? How can they be relatively prime? How can be their GCD 1? If 2 is a number which comes in factorization of p and q both. So that is a contradiction. So that is a contradiction here. It means that our assumption, the step where we denied, that is wrong. So thus we show that root 2 is not rational. So there can be like a lot of examples like we can bring through this approach. So what questions you have? Like instead of saying any questions, I prefer to say what questions you have. Because I believe that you have questions. Yes? Oh, sorry, please ignore that. That is Startling approximation theorem. Please ignore that. That was my mistake. I shouldn't have brought that. Startling approximation theorem. There are various forms of writing, various versions. But this is very useful. So there are several versions of this formula. But yeah, this is very useful. This is used in a lot of disciplines. Yeah. So, any questions before we end the session? Yeah.
So, sir, any conjecture can be proved by both the methods, induction as well as.
No, our way of proving the proofs is not, this thing is not exhaustive. We'll be talking about other techniques as well, like proof by cases, proof by contraposition. We'll be talking about those things in further sessions. But this list of these usual general techniques, that is not exhaustive. That is not going to work for anything. No, we cannot guarantee.
But sir, what if this thing is proved by contradiction? Can we also prove it by induction?
Sometimes it's like there are like sometimes I think like it doesn't make sense to apply a particular technique. There can be instances, but I can't say as of now. Like there are sure, I think that is what I believe. Huh? Yeah, of course. I think that like if you talk by prove by cases, how will you prove this thing? I don't know. There can't be proofs like because of the definition of irrational numbers. We just simply define anything is not rational, that is irrational. No. Yeah, that is not making sense here. That doesn't make sense at all. Induction. Yeah, anything? Yeah, please say. Yeah, we are like hoping your contribution. Like after this session, there will be lunch break, and then there will be an activity session which we are calling tutorial sessions, in which like there will be groups of 10 or fewer than 10. So with a person who will be accompanying you, like who will be facilitating your discussion. So like we want your contribution, we want your questions. So if you have anything to share, please do not hesitate. Yes? You can't say that. How can you generalize that? Like this technique is more effective than that.
In case of proof to not rational, we directly use proof by contradiction. Like that can be just built.
I think that this is my idea. There is one thing, like we say that anything proposition is it's true or false. That is what we say, right? That is what we were talking in the morning. See, like people are going beyond that. Like when we talk about fuzzy logic, like they talk about like there should be something in between true and false. But here we are talking about either rational or irrational, nothing in between. When such kind of things comes, this is called method of excluded middle. Like it means that there is nothing in between. When you have such kind of thing, then I think method of contradiction will work in most of the cases. Like you are just, there are only two cases, rational or irrational. Like of course there are other types of numbers as well. You will study transcendental numbers. We are not going in that thing. So we have presently rational and irrational. So I assume the opposite, arrive at contradiction, then I'll say that this is the only possible thing. So there are two possible things only. And in those circumstances, usually this method works. Yes. Does it make sense? Yeah.
The contradiction method, we tell that since there are only two outcomes, the other outcome is obvious because one is ruled out. But how can we rule out that there is no more outcome for that?
Yeah, that is what I was saying. This is our assumption. Method of excluded middle is our assumption. There are mathematicians who do not believe in a method of excluded middle. I was talking about fuzzy logic. Fuzzy logic, it talks about degree of truthness. It's 0.6, like that's kind of a probability kind of thing you would find there. So they don't believe, like that's a debate. That is what philosophy of mathematics, like people debating. So there are several schools of thoughts. So traditionally, like in traditional textbooks, this thing is generally adopted, like by most of the people. They like agree with true or false. So you'll be having like such kind of ideas in upcoming classes. A series is convergent or divergent. Nothing more than that. So you are not talking about other behaviors of the sequence. So there are disadvantages as well, because you are not talking about other behaviors other than these two. You have simplified your case, so you are not considering the complexity. So that's why, like I am assuming that these are the only two possible cases, rational or irrational. So because I have defined irrational, how I have defined any real number which is not rational is irrational. So this is a very simple version. Yeah.
One is neither prime nor composite. Is it the logic or the method of excluded?
Any number, which number you are talking about?
One is neither composite nor prime.
That is your assumption. That is like we say that there is a very interesting thing which we call axioms. Modern mathematics, and even not only mathematics, nowadays, like a lot of things we talk in with the help of axiom. Axiom means our rules. Like we are playing a game and we are setting some rules. So like if I am playing cricket, so when I was like a child, like our siblings, we used to play cricket on the roof. And my mother used to like we were just like, and our neighbors as well, when they were not so good enough that when the ball goes to their house, they didn't return. So we changed our rule there. We changed it to like if the ball goes there, you will be considered out. So that is our rule, that is our axiom. And maybe your neighbors are great. Your axiom, you might not consider it as an axiom. So nowadays, what we do, this is very interesting. Yeah, see, listen. So we have several axioms. We have rules to play the game of mathematics. And it's not that whatever comes to my mind, that becomes a rule. Every rule that we consider as an axiom, that has some rationale to make that game interesting. So when we talk about Duckworth-Lewis rule, there are set of rules there, and they are changing. So Duckworth-Lewis rule is changing. Like you are just according to the situations, you are making adaptations to the new settings. So this is what like this, you are saying that one is neither prime or composite. There is no proof for that. There is no proof for 0 factorial is equal to 1. This is an assumption so that it follow the structure, that formulaic structure. This is, I think this should make sense. Like the natural number, see, the natural number we start, how do we start? 1, 2, 3, 4, like that. Like Peano was a mathematician who assumed 0 as a natural number. There are several cultures across the globe who still consider 0 as a natural number. But there is no harm in considering 0 as a natural number or not. That is just like that was the first Peano axiom. But nowadays, usually, it's widely like we start with 1. Yes, any last thoughts? Yes, please. Sorry.
How do you judge how elegant a proof is?
Oh, elegant is a very subjective term. So I think like it varies. Like for me, like there is a mathematician like Terence Tao. Terence Tao was a field medalist. Field medal, anyone of you knows about field medal? Yeah.
It's a medal given to leading mathematicians who've done work and they're under the age of 40.
Yeah, this is like considered a Nobel Prize in mathematics. So Terence Tao, he has a blog, terrytao.wordpress. There is an article, he writes that math is beyond rigor and proofs, where he talks about intuitive ideas. He talks about for some people, like if you are pictorially proving things, for them it makes sense. And they found those proofs as, they prove elegant enough. So, but there are people like G.H. Hardy. So, there are like different kinds of people and different preferences. So the elegance like kind of thing that varies from person to person. But one thing looks common, that you should have some logic, your laws of logic that you must employ while proving something. So there should be some consistency. It shouldn't look like that in one example you are like, according to your convenience, you are saying this thing, and then according to your convenience you are modifying your laws. So there should be some consistency in your laws of like putting things. And how do you infer? So
Yeah. So in the Riemann hypothesis, in that you found that almost every prime number falls on the biggest, but still it's said that it's not true, and it's not been proven yet with mathematical rigor. So isn't that taking mathematical proof a little too far? You can just assume it's right because check so many numbers.
Yeah, sure. Riemann hypothesis is a long-standing problem. This is one of the 6 problems proposed by CMI. It's not Chennai Mathematical Institute. It's Clay Mathematical Institute, who for each problem there is $1 million problem. So Riemann hypothesis is one of them, and it talks about prime numbers. So, and it hasn't been proved yet. See, these things, they bring new things. Like if you're like 9th, do you follow NCERT textbooks? So 9th class, there is a chapter, Euclid Postulates. And at the end of the chapter, it talks about like the cases, like when we say that the sum of angles in a triangle is 180 degree. So, but it may not be true. If you draw a triangle on a ball, if you're sitting inside the ball, so the angle, the sum of angles, it's less than 180 degree. And if you're looking from outside, it will be greater than 180 degree. So they talk about spherical geometry there. So because in that thing, they were talking about Euclid's 5th postulate. And Euclid was trying to prove that, but he couldn't. And upcoming mathematicians also couldn't. So just like these such kind of things which we cannot prove, they also bring new theories. The spherical geometry was a great development. So yeah, Riemann hypothesis is one of them. Yeah, of course, we have not been able to prove that, but that doesn't indicate any shortage or any negative thought. It helps us think continuously about that and bring new theories and new ways of proving things. So we'll continue this discussion, and right now this is time for lunch, and yeah, we want to have an engaged discussion rather than lecturist kind of thing. And I want you to, like, don't hesitate at any moment during this event to say anything. Nothing is right or wrong here. Just say. So don't say that it's like, don't think that you are asking anything which might not be worthy enough. So if you are thinking, a lot of people will be thinking. So yeah, thank you for this session. So see you outside.